start this part 2 video on compound interest, finishing up the activity we were looking at, we left off with making a prediction as to how much might be in the account B after 50 years when it's compounding a 10% interest every year for 50 years. So, in our previous scenario, we're going to see a demonstration of the power of annual compound interest. The account is earning interest on the interest. So the general formula for the compound interest can be recognized by following this pattern. We have 100 times 1 plus the rate, 10%, which gave us our first amount, $110. We ended up, for year 2, well, it's going to be $100 times the interest, times, or 1 plus the interest, times 1 plus the interest. And we can rewrite this. And this right here, because we have it repeat, we could rewrite it as 100 times 1 plus 0.10 squared, because there's 2 of them multiplied together. That's kind of the definition of exponents, right? Repeated multiplication of the same thing we can represent with exponents. And that gave us our $121. Now for year 3, we had 3. So I can rewrite that as 100, our principal, times 1 plus the rate, 0.10 to the 3rd power, which equals $133.10. And then we see this pattern continue. So finishing off, we can see, and I rewrote each formula for years 3, 4, and 5 using the exponents. I'll underline that here, here, and here. Okay, so we end up getting this repeating factor every time because the interest earns interest. And so if I have 3 years and it's compounded, then the interest from the first year earns interest on the second year, and it earns interest on the 3rd year. And the second year's interest also earns interest. So the money is just making money. It's a cool concept. So now, we're going to take this pattern that we notice, and we're going to write a general formula with some variables, where P is our principal or initial deposit, rate R is our interest rate, and T is our time in years. Okay, so here we go. We end up having the amount in our account equals our principal times 1 plus our rate to the time. Okay, so now notice this was compounded and annually. And we'll see examples later on where I have different types of compounding interest. But we can use this general rule to figure out what's happening when we compound interest annually. We're going to use this general formula to calculate the future balance of account B after 50 years. So we end up having the amount in account B. I'll write a little subscript of B there to make sure we know that we're talking about what's in account B. It's going to be equal to 100 times 1 plus 0.10 to the 50th power. We use our scientific calculator to calculate this. Now you can type this out, just make sure you put this part in parentheses, and then you use the caret button to do the exponent. Okay, the caret button looks like a little up arrow. I think it's like 4 buttons below the second button on the top left. Anyway, you type that into your scientific calculator and you get that the account B's balance after 50 years is $11,739.09. Comparing that to $600, which one would you rather invest your money in? I hope it's clear. But if I have the choice to earn $11,739.09 or earn $600 by just investing $100 into an account, I'm going to go with the one that makes me bank. Okay? So, compounding interest is awesome because your money makes money. There's a couple of things for us to note. Interest is often compounded more than one time per year. There are different types of options in the way that interest could be compounded. It could happen monthly, which would be 12 times a year, quarterly, which is 4 times a year, semi-annually, which is 2 times a year. You could also have it be daily, or what we would consider continuously. Okay? So we're going to adjust the previous compound interest formula to create a more general formula that will calculate interest if it's compounded in times a year. So what we have to do is we have to think about this. We're taking our annual interest rate, but we're dividing it amongst a certain time period. So if our original interest rate is R, and we want to divide it by a quarterly rate, or divide it amongst 4 times during the year, we would take that rate and we would divide it by 4. Okay? So, our rate, we would now represent as your rate divided by N, which is the number of times the interest is compounded per year. So, in this formula we just found, R to the T, the rate here gets replaced with R divided by N. We also need to adjust the exponent, because how many times would we compound the interest in, let's say, 3 years? So how many times would the interest be compounded if we were compounding it 4 times per year for 3 years? That ends up being 4 times 3, which equals 12. So our new exponent, which tells us how many times it was compounded, okay, we would rewrite the exponent as N times T. Okay, so I created this little colorful chart to represent our compound interest formula in general, if it's compounded in times. Okay, where N could be once per year, it could be 4 times per year, it could be twice per year, it could be 12 times per year. So our compound interest formula is A equals P times 1 plus R over N to the NT power. Okay, so I've labeled each part. A is the amount that accumulates in the account. P is the principal, or your starting amount. The R is your rate, your annual rate, that's written as a decimal. The N is the number of compounding periods, because your rate would be divided amongst the compounding periods. And then the power would be N times the time in years. Okay? Because if you compound every 3 months or 4 times a year, the number of times your interest is making money on it would be the number of times it compounds times the years. So let's take a look at this again. I'm going to write that formula. A equals P times 1 plus R over N to the NT. You need to know this formula. Okay? And we're going to look at account C, which has the same annual interest rate of 10%, but it's compounded quarterly. And it's going to have the same amount of money invested, so it's going to have the same principal of $100, the same annual interest rate of 10%, but it compounds quarterly. So our N equals 4. So let's use this formula. A equals 100, our principal, times 1 plus 10% written as a decimal divided by our number of compounding periods to the 4 times 5. Okay, now I can actually do 4 times 5, that's 20. So my exponent is a 20. And then we can use our calculator to calculate this value. So we're going to do 100, open parentheses, 1 plus, and you might want to put parentheses around this just for posterity's sake, 0.10 divided by 4, close parentheses to the 20th power. Remember to use that caret button on your calculator to show that exponent. When we do that, we end up getting $163.86. We're going to round to the nearest cent here. Okay, so let's compare that though. When we looked at year 5 for account B, we ended up having $161.05. So by compounding quarterly, we end up with over $2 more in our account. So the more times it compounds, the interest compounds, the better, or I guess higher, the amount in the account is. Calculate the amount in the account for account C that compounds quarterly over 50 years and figure out how much money would be in that account, and then compare that to account B. We could do the same thing if we have an account D. It has the same annual interest rate, the same amount of money invested, but it's compounded monthly. So N equals 12. So that would be A equals 100 times 1 plus the 0.10 or 10% divided by 12, and then to the 12 times 50 as your exponent. Now 12 times 50 would be what, 600? And so you're going to get a big old answer. Getting $14,536.99. Now remember to round to your nearest cent. Okay. So the same amount of money is invested in account E with the same annual interest rate, but it's compounded daily. So our N value, and we're going to use the banker's rule on this example, our N value will equal 360. So I'm going to leave that to you to calculate because I want to make sure we move on and kind of summarize what we've seen. We've considered the previous scenarios where $100 was invested at 10% interest for 50 years, and we had different amounts in each account after 50 years. So for simple interest, we had $600 at the end of 50 years. Okay, compounded 1 time a year, we had $11,739.09. You can do compounded 4 times a year, 12 times a year, and 360 times a year or daily from our examples that we just saw. So fill in the rest of this chart. But then we have this situation where we have something compounded continuously. So we're going to address that in just a minute. Now, if you were to graph these numbers on a number line, okay, let's say zeros here. Let's count by 500s. It's not even fit. It's not going to fit. Because in order to get to $11,739, I'd be way off the page. So let's rewrite our number line. Let's do it in terms of thousands. 2,000, 3,000. Now on a real number line, these would be equally spaced. 4,000, 5,000, 6,000. I'm still not going to have enough space. 600, which would be less than half between here, so that's a simple interest rate. And then the next one, when we have compounded 1 time a year, or 1 time a year, is at $11,739.09. And then the next few are within this range. You can look at our examples again. We had that compounded 12 times per year was over 14,000. So you can see how there's a huge jump from simple interest to and compound interest when you're looking at long periods of time. As it increases, that interest is compounded more frequently. So what happens to the future value? Well, that means since the interest is compounded more frequently, the money keeps making money more frequently. So you get more and more and more. And so the future value is going to be significantly greater. Sometimes it's not as significant if it's not over a large period of time, but it will absolutely be greater than something that is compounded less often. Okay, so our last big concept for this is, I think, one of the coolest concepts here, and it involves one of my favorite numbers. If you're interested in it, you can ask me about it, and I'll send you a video that I really like. But for something to be compounded continuously, okay, we actually have a separate formula to represent this situation, and it uses the letter E, which is our irrational constant. So this formula is going to include this value, which looks like a letter, but it's a letter representing a number. And this number is 2 and some change. So an irrational number is a number that cannot be represented as a fraction or a non-repeating or terminating decimal. And so one of the most familiar irrational numbers would be pi. And people think, oh, pi is 3.14. But pi is not 3.14. It's 3.14159,626, and it goes on forever and ever without any repetition. Okay, not that the digits don't repeat, but there's no pattern to the repetition. Okay, so E is a number like pi that is irrational. It shows up in many applications and kind of cool applications, but we actually see it occur when we compound interest continuously. And the way we find that is we take the principal times E to the RT. There is an E with a caret, and so if you have a problem that is being compounded continuously, you can use the E button on your calculator to actually substitute in that number for you. So we're going to look at the same amount of money is invested in account F with the same annual interest rate, but it's compounded continuously. So we're talking, we have 100 is still our principal, okay? Our rate is still 10% or 0.10, but it's compounded continuously for 50 years. Okay, so we're going to say A equals P, which is 100, times E to the 0.10 times 50. This, and we get that the amount in the account after 50 years is $14,841.32, since this will round up to 2 cents. Okay, so this number is going to be the largest value on our number line. Okay, so check that out. Look at our previous number line. Fill in the one for 360 times the daily rate, and then also add this one to it, and you should see that this is the largest value. We have several more, or a couple more examples. I'm only going to go over one of them, and I'm going to leave the rest to you. If you have questions, you can always reach out and let me know. But let's suppose that we have $3,000 invested at 5% interest and it's compounded continuously. How much would you have in the account after 4 years? So we're going to need to use our compounded continuously formula, which is A equals P times E to the RT. P is 3,000. R is 0.05, because it's 5% written as a decimal. and the time is 4 years. So we're going to substitute all of these in. 3,000 times e to the 0.05 times 4. And what we get is $3,664.21. Okay. Now try number 20 on your own. It continues onward. Okay. So you can see if it's compounded 1 time per year, quarterly, monthly, daily, and then continuously. Inductive reasoning to figure out if this is a pattern, if that we can expect a certain outcome depending on how our interest is compounded. That concludes our compound interest videos. If you have questions, please make sure that you email me and let me know. Thank you.